Let's talk about compound systems. A compound system is one where there is a series of systems in a row, like you see here in the diagram. This is pretty common in signal processing. You're rarely ever processing a signal with just one system. Usually there's a signal processing pathway and your signal has to go through more than one subsystem in order to get from all the way from input to output. So we've learned before that every time your signal passes through a system, then you're just going to multiply the Fourier transform of your signal with that of the transfer function. So in this case, we can work that out to say that the output signal y of j omega has to be equal to it's just going to be a straight product. So it's going to be the first transfer function times the second transfer function times the third transfer function times the Fourier transform of the input signal x of j omega. Okay, because they're passing one from the other to the other, you're just going to multiply. And again, we're going to multiply magnitudes and add phases. So for example, if x of t was, I don't know, let's just say it was some cosine at, I'm going to pick a number arbitrarily, let's say 25 rads per second, then the output would be, it would still be a cosine at 25 rads per second, but its magnitude would be adjusted by the magnitude of h1 at 25 times the magnitude of h2 at 25 times the magnitude of h3 at 25 times cosine of 25t plus the angle of h1 at 25 plus the angle of h2 at 25 plus the angle of h3 at 25. That was a mouthful. Okay, and that's a 3. All right, so you get the idea. You just you're constantly multiplying the magnitudes and adding the phases. However, we do need to be careful about one important thing, and that is that the above formulation only works as long as the systems don't affect one another. Okay, so we have to make sure that the systems don't affect one another. And let me show you what I mean by that. Let's take a very simple system. Okay, what could be any simpler than a voltage divider? So here's a voltage divider, and you could think of this, let's say we make them both 1K resistors. We could think of this as a system, which I'll call H1, and it's going to have, there's no frequency dependency here. We can just read right off the numbers that it has a constant gain of 1/2. Okay, now let's have another system. Let's have another system with, I don't know, I'm going to pick slightly different resistor values for this second one. Let's have it be 1K and 2K. Now this is also a system which doesn't depend on frequency. It has a constant gain of 2/3. Okay, so the question now is what happens if I put them in series? Okay, so what happens if I do this one and this one together? Okay, H1 and H2 in series. So 1K, 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 2K. Now here I have a problem, okay? And the reason I have a problem is that when I was coming up with my formula for H1, when I was doing my voltage divider, it worked on the assumption that all the current through the first resistor went through the second resistor. And likewise when I did H2, I was working on the assumption that all that current goes down there. Now, once I've combined them together the way I have, this is no longer the case. Now I have all the current that goes to that first 1K resistor doesn't all go down to the bottom 1K resistor. Some of it goes there, but then some of it goes into the right-hand branch as well. Okay, so now effectively the systems are affecting one another. Okay, that's where the affecting comes into play. Effectively, I've changed the flow of current. So essentially, I can do one of two things. Okay, so first of all, let me just point out that in this specific case, H3 does not equal H1 times H2. I have two choices. Okay, the first choice I have is just to solve H3 as if it was its own system. Okay, so in other words, let's see if this is my V out and this is my V in. I've really got a voltage divider of a voltage divider. I can work out the current equations and the voltage equations and solve for V out, and I've done that. And if you do that, it works out that H3 equals, if my math is right, it should be equal to 3/7. Okay, H3, meaning the output should be 3/7 as big as the input, which is not the same as H1 times H2. Okay, again, I got 3/7 by just solving the current and voltage equations and solving the system of equations. I'm not going to do that on the paper. Everyone should know how to do that, but that's how I got it. So that's one way of doing it. The alternate strategy is to make them not interfere. So the alternate strategy is remove the interference. And that's going to require a little bit of elegant circuit building. In the case of the example that we're talking about, one way to do it would be to separate the two circuits with a voltage buffer, which is an op-amp that's connected as such. Okay, that's 1K and that's 2K. And when you do this, as you recall, no current can flow into an op-amp port, which means that all of the 1K current is still going to have to go down through that resistor. Okay, so that's still going to give me a gain of 1/2. Okay, so there's not going to be, none of that current is going to branch into the second half of the circuit. And then likewise, all of that 1K current is going to go through the 2K, so that's still going to give me 2/3. So in this case, I can say that my gain is going to be, I guess we'll call that H4 because this is a very different system. This will in fact equal H1 times H2 because they don't interfere with each other, and I'm going to get a gain of 1/3. All right, so just be mindful of how these things work, but at the end of the day, we're just multiplying transfer functions together.